Hey coders, welcome back. This is our assessment 18, I guess. I don't exactly remember, but yeah, let's try to go through one of these assessment once again and try to solve questions under them. So if you don't know, LeetCode has this mock assessment stuff. So here, basically, you can choose either from online assessment, phone interview, or on-site interview, and it basically contains like two three questions randomly, right? And basically can simulate try solving those questions under a constraint, right? Time constraint. And this is good because the questions are here are pretty standard, and they are the questions which is being asked in different companies, right? So yeah, that's what I've been doing on this channel. So like I have, I think, 16 17 video. So today again, let's try to go into this on-site interview one. So there might be four questions. So it says like we gonna have like 3 to 4 questions, right? And we have to solve it under 2 hours. And for each question, if I'm able to solve, I always go through and explain what are the prerequisites needed for that question. And if you don't know about that algorithm or data structure, you can of course read from the internet. So let's start. So yeah, we have like here 3 questions, and yeah, let's try to solve. Okay, so I hope this light theme is okay. I need to change it, but okay, no worries. Let's go with the light theme for now, and maybe later we can do that. So let me zoom a bit, maybe. I hope this is visible. Uh, okay, one second. Let me set my screen. Yeah, I think this is good. Yeah. Okay. Let's try to solve this first question where it says like given a non-negative, return the square root of x, round down to a nearest integer. The return integer should be non-negative as well. You must not use any built-in exponent function or operator, and you do not use this. Okay, so basically you do not have to use any built-in library from your programming language, and you have to find the square root of a number. Now, for example, here it is 8, right? So, what is the square root of 8? It's nearly like 2 point something, right? Because if you take 3, so 3 is 9, so that is greater than 8, right? So, it's something below 3 and greater than equals to 2. And that's why you see here it says like 2 point something something something, and the square root of this 8 is like 2. We just need to take the floor of it. Um, okay. So, I mean, if you see the question like this, I don't think I think you should have studied this kind of question. I think there is a no any particular way to identify it. Like this is a binary search problem. Because generally, if you stay in the library or if you solve some questions, you will see that um, finding exponent or finding square root can be done in a logarithmic time, and that is the optimal. So that's thing I know. Now to solve this problem into the logarithmic time, most of the time either it's like a divide and conquer algorithm or the binary search. Even divide and conquer based algorithm are also like a binary search because ultimately we are dividing that whole search space into the half and half and half, right? So what's the idea for solving this problem? So it's kind of like divide and conquer. How? Let me explain. Okay. So let's say we are trying to find a square root of maybe 16, right? So the idea is where the answer can lie for 16. It can lie from 1 to roughly around maybe 4 because, or maybe I can say 16. I mean, why not, right? I can take the search space like this. I'm 100% sure that 16 square root will lie between 1 and 16. So this is the first thing you have to assume. Let's say we are trying to find a square root of 100, right? So what's the search space? Since it is like it can be non-negative, so it means basically from 0 to anything else. And what's the search space for 100? It can be, meaning the square root of 100 can lie between 1 to 100, right? And now we apply binary search to see whether it is the square root or not. How? So let's take any number between 1 and 100. Let's take maybe 30, right? So let's choose like 30. Then we do 30 into 30, right? So it gives me like 900. It is way bigger than this 100. So what does it mean? It means that we have chosen some number that is very large. So we have to reduce our search space. So since we already checked for 30, so we know that any number that greater than 30, maybe 31, 32, 40, 50, 60, 70, all those squares will be greater than 100. So it's not a good idea to go into and trying for other number that are greater than 30. So what we can do? Now we can reduce our search space to go from 1 to 29, right? Because we know we already have proof, right? For 13 to 3900, so way bigger than 100. So maybe we should try between 1 to 29, right? And let's take another number, maybe in between this 1 and 29. Let's say maybe 15, right? You can, of course, we will do the middle element like we do in the binary search, but yeah, let's do 15. Now 15 into 15 is 20, 225, right? And again, it is very bigger than 100. So what does it mean? Any number that is greater than 15 and less than 29 will not be the answer, right? Because all these numbers will be greater than 225, right? Because if you take 16, 17, 18, 19, 20, 21, or 29, all these squares will be way greater than this 100. So what we're gonna do? We again reduce our search space now from 1 to dot 14, right? Because we already checked. Now again we're gonna check some number, maybe let's say 5. So 5 into 5 is 25, right? Now 25 is less than 100. What does it mean? It means we have to increase our search space greater than equals to 5. So our next search space will become from 6 to 14, right? And that, so this is the idea of this problem for solving this kind of problem. Um, so I hope this one is clear. And this is how, of course, in even if you see in your programming language, the logarithmic square root method implementation, you will see something like this. Either they're gonna use a binary search or maybe some other optimization, but yeah, this is the base idea for this one. So yeah, let's solve this. So again, we write our typical binary search, and again you see here the constraint says x can be from 0 to something. So we know that if x equals to 0 or x equals to 1, we can simply return x, right? Because square root of 0 is 0, right? Um, square root of 0 or 0, I'm not so. I think that will be some imaginary number. I don't know. But x is equals to 1, we can return. Let's see. I'm not sure about it, but yeah, let's that to be our base case. And left equals to 1, and right we are choosing x, right? And x can be from 2 to the power 31 minus 1, so it can be assigned into the int value. So we are good. Now again, we do our binary search, like, and then we gonna. So this mid is basically I'm choosing some number, let's say 30, 40. Generally, we take the mid of one. So let's take that. Okay. And then we're gonna check if mid into mid. So what we need to find out? We need to find out a number that is just greater than or equals to this 4, right? So mid into mid is greater than equals to x. If this is the case, we're gonna reduce our sample space because we are going way beyond, right? Otherwise, we can say left is equals to mid plus 1, right? And then I can check. Now left will contain me the minimum value where this constraint is getting success, right? The mid. So if you try to write your own binary search, you can find it. I'm writing this binary search and answer approach, and I'm pretty comfortable with this one. So yeah, even you can write your own binary search, whatever implementation you like. Now I can just check left into left. Um, equals to x question mark. If this is the case, return left, else left minus 1. Because otherwise, um, maybe some number that is greater than left, and we need to make sure that we are returning the correct left. For example, here it might go to like 3, right? Because 2, it is possible. So for x is equals to 8, if we choose 2 as my answer, the 2 into 2 is 4, and 4 is fine, right? According to this logic. So we will go in the right side. So from 3 to 8, we try to find out the answer. And in that case, we're going to return 3. But 3 is not going to be our answer. Our answer is going to be something less than equals to 3. So yeah, let's try compiling it. See any compile time error? No. Let's submit it. Okay, we have one wrong answer. Okay, so I mean, if you see these kinds of numbers, something that is very large, you know something is going out of bound. That's for sure. And where it can be possible here, right? So mid into mid, we are multiplying. Now this mid can be integer at max value because 2 to the power 31 minus 1. So we need to typecast this into long. Otherwise, we will mess up. So let's convert this into the long, and mm, even this one also, I think 1L R. I think yeah, this will be fine. Let's try adding running for this test case and see. Okay, we are getting 4639. Okay, let's submit it. So these are the small mistakes. I mean, right? And you have to be very sure with your numbers, right? So because x is here like 2 to the power 31, right? And when I'm doing this mid into mid, of course it will go beyond the integer limit, and that's why it was failing. So I just typecast into the long. I just multiply with 1L, or you can typecast using that parenthesis syntax, right, and pass long in it, and that should also work. So I hope this one you like it. Let's move to the second question. Uh, okay, let me remove. Okay, no, I think I need to see this structure of a node. Okay, so given a binary tree, we have something like left, right, and what is this next? Populate each a next pointer to a point to its right node. If there is a no next right node, the next pointer should be set to null. Initially, all next pointers are set to null. I don't understand. Given a binary tree with this structure, populate each pointer to the point to its next right node. Next pointer to. Oh, okay. Okay, I think I got this. So this is the tree, and um, what 1, 2, 3, 4, 5, and null, and then 7. And for each node, we're gonna create a next. Basically, we need to change the pointer. Okay, populate each next pointer to the point to its next right node. Okay, so for one, its next right node is nothing, right? So for two, the next right node is 3. For 4, next right node is 5. For 5, next right node is 7. For 3, there is nothing. For 7, there is nothing. Okay. And we have to, I think, return the tree. Yeah. Okay, let me hide this thing. I just need to see this here. Rest will be fine. Okay. Okay, so question says, so for every node, we gonna have this left pointer, right pointer, and a next pointer. and we need to assign the value in the next pointer to the whatever the right element is there. So for example, one, there is a no, it at this level, there is a no right node, right? Nothing at this level in the right side for this one. For two, the right side node is like three, right? So we can appoint two to three, right? For four, the next right node is five, right? For three, and then another, there is nothing, right? And for seven, there is nothing. Okay. The constraints is like 6 into 10 to the power 3. So maybe you can write a like n square solution. That will be acceptable. But okay, the very first thing I notice is like it's kind of like a level out of traversal because so we are doing something on each level. Of course, we can solve it in DFS also. You just need to make sure we are okay. So maybe what I should do, um, I should do the level order traversal. So maybe I will get like here 1, then this is 2, 3, and this is 4, 5, 7, and then I will iterate from the right side, right? And then check, do we have anything in the right side? No. Do we have anything in the right side? No. Do we have here? Do we have here? Do we have here? Uh, 7, nothing. 5. Okay, okay, yeah, this is, I think this is easy. Let me explain what it is saying. So the idea is I will first at each level I will extract the node one by one. So at level 0, right, at this root level I'm gonna have 1. In the next level we're gonna have 2, 3. In the next level we're gonna have 4, 5 and 7. Right, for this tree. Now for this one I think for this one now let's try to focus on this one. So I will iterate from the very right side. Maybe I can put this thing into a queue or something, list maybe, and I will iterate from the right side, right? So from 7, I will say, do we have anything in its right side? No. So we don't need to do anything. For 5, do we have anything in the right side? Yes, yes, we have this 7. So I just need to make sure 5 dot next is equals to 7. Similarly for 4, what is the right side? 5. So 4 dot next is equals to 5. And I think that should work. And even the constraint is pretty relaxed. So n square solution will be possible. So I hope this is clear, right? So I'm at each level. So we will do the level order traversal. So for this level, let's say 2, 3, right? Now I will iterate from the right side. So 3, do we have anything in the right side? No. For 2, do we have anything in the right side? Yes, this 3. So I can just make 2 dot next is equals to 3. And we will make the changes in the same tree. And so we can just return the root as our answer. Yeah, I think this is it. Okay, let me write the code and then maybe I can explain one more time. Oh, it's like this. Okay, so what we need. Um, okay, so I hope you know the level editor was like the BFS on a tree. So maybe I can write here prerequisite uh is BFS on tree. Anything else we need? No, I think this is it. This is the only prerequisite for this problem. And so for if you know that this is a level order traversal, we need to have a queue, right, to simulate that level order traversal thing. So I'm gonna create queue linked list and I will offer my root into it. And also root can be null. So if root equals to null, just return root, right? So if it is a null, just return null, right? And this is we are adding this. That's fine. Now simple BFS not equals to uh, equals to oops, not equals to 0. We're gonna get the size of the current element, right? So like at any moment my queue will either contain this one or this 2 3 or this 4 5 7, right? Like this here. So I can just say a size which is queue dot size, and then maybe I can create Or okay, maybe I can just instead of putting the left child first, I can put the right child, and then I can keep track of previous. I mean, yeah, that will save some time, but I think that will be a bit messier. Um, but it's not a bad idea. Even if I iterate two times, it will be still the linear. So I can just write something like this. This will be more readable, simply. New linked, maybe array list, and I can say like for I less than size I plus list dot add uh q dot poll. Okay, so this is I have extracted the element like this 4, 5, and 7. Now what I need to do is I need to do that mapping, the next thing, right? So for int I equals to list dot size, maybe I can I know the list will be of the size, so I can run a loop again, not from zero, from opposite side, right? Because we have to choose elements in the right side. I have to do something like this from opposite side, and I can just say if I equals to size minus one, I can simply can extract the node maybe war node list dot get I can say if this is the last extreme right element, just then just do like node dot next equals to null. I think by default it will be null, but yeah. Else, what we need to do is we have to do like node dot next is equals to list dot get I plus one, and yeah, this is it. And then also we also need to make sure we are pushing all these neighbors also. So, what I messed up something? No, I think it looks good. So this is the node. We are pulling all these nodes, and here we also need to make sure we are adding these childrens, right? So for two, it's children. For three, it's children, right? So I can just say like, I can extract the node maybe var temp q dot poll, and here I can say temp, and then if temp dot left is not equals to, why I'm typing this null not equals to null, I can say q dot offer what temp dot left, and similarly if temp that right is not equals to null, q dot offer temp dot right. Here I missed my equal sign, and then from this thing, I'm extracting the yeah, looks good. Looks good to me. I will see. Okay, and then I can just return the root because we have modified the same tree. So okay, yeah. So what we're doing, so for this level, let's say we 2, 3, and the second iteration, right, in this while loop. So size will get is 2. Then I'm iterating over all of its elements. Basically, I'm extracting from the queue. So 2 and 3 will be extracted and get put into this list, right? So 2 is there in the list, 3 is there in the list, and also we have added this left child, right child, left child, right child, and then I'm just again iterating into my list. And for 2, 3, so 3 so for 3 dot next we put null, and for 2 dot next we're gonna put the extreme, just its right element. And I think they should work. Yeah, let's compile it. See any compile time error. Okay, we have one compile time error. I missed the angular bracket here, the generic one. Let's try again. One hashtag, two, three hashtag, 4, 5, 7 hashtag. That looks good. let's try. Okay, I think let me check for null section other empty list. Uh, I think this is good. Why they have given no dot value -100? Is there anything we can do about it? No. Let's submit it. Yeah. Okay. So yeah, only prerequisite is if you understand the BFS on a tree, you will be able to solve this problem. And rest of the thing is just a simple iteration and little bit of for loop, right? And nothing else. So I hope you like this one also. Let's move to the third question. Okay. So I mean the questions says like sliding window. So of course you should know sliding window, right? And one thing I will give you if you are just starting with it, whenever you are creating different pointers, no, try to create with the same name. I mean, it's just for your memory, right? For example, let me show you one thing. I mean, these are things I did when I was learning. So, for example, for any left or right pointer, I generally create two variables, left and right. Some people create I, some people create J, but I would recommend try to create same variable, especially if you are just starting out. It will basically help in retaining the knowledge. Trust me, this works also. So even if you see my previous binary search and all questions, I generally make variable naming kind of same. It just help you retain the things, whatever you are learning. So yeah, let's see for this one. So we are given this array of nums. There is a sliding window of size k, which is moving from left of this array to the very right. You can only see the k numbers in the window. Each time the sliding window moves right by one position, return the max sliding window. Um, Max sliding window meaning okay, I think just we just need to return the max element, right? So 1, 3 minus 1. So max is 3. 3 minus 1 minus 3, max is 3. Then minus 1 minus 3, 5. Max is 5. And similarly, dot, dot, dot. 5, 7, 3, 6, 7. Okay. Okay. So I don't know in which of my assessment. So we try to solve this question first using a priority queue. And that time it was giving us TLE because of course removing an element from a heap is like a logarithmic and it required us to like solve that problem into a constant time and then we introduced like monotonic queue. So I think this is the same problem. I will again explain the all the logic. Maybe I should try first using priority queue because that is easier to explain, but we might get TLE on seeing the constraint. Um, okay, let me first try to explain this sliding window, how I write, and of course you can write in your own way. So maybe I can just write a template here. So the very first thing you should do is, how can I explain this one? Um, Maybe from instead of determining the max number here, like in this, like in every cage equals to three size window, like this window and this window and this window, we are trying to find the maximum value. So instead of finding maximum, let's say we wanted to try to find the sum of these elements into this window. Like so 1, 3 minus 1 sum, then 3, 1 minus 3 sum, then minus 1 minus 3 and 5 sum. And I will explain that and then we will later to go into this max thing. Right. So I'm just giving you my template how I generally write it. So let me copy this thing. Okay, so the very first idea is we need sum of all these window. Not in the question. In the question we have to find the max, but for now let's imagine for this something, right? So we need to find sum of every window. So initially my sum is 0. What I'm gonna do, I'm gonna first simple. Just focus on this initial window, like 1, 3, and -1, right? So what need to be done? We just need to do something like this: I is equals to 0, I less than k, I plus plus, and sum plus equals to, uh, let's say this is nums of I. So this is the step one, and you have to write. This approach is feasible for almost all the cases. So initially, we just focus on this window, and then the next step is step two is we're gonna create a for loop, something like this. I will explain why this is. You will see many people like while loop and other things, but for fixed size sliding window, I generally use this approach, and it works most of the time. Now, what's the idea? You see, we already have the sum of this window, initial window 1, 3, and -1. Now, what we'll do, we need to find this window sum, right? So, if you see carefully, we are just appending this -3 into our window and we are removing this one, right? So, what does it mean? It simply means our sum, whatever sum we had previously, like from 1, 3, and -1, we are appending this -3 and removing this 1. So this simply means sum plus equals to nums of right and sum minus equals to nums of left. Now, for the very next window, for this window now our sum has the answer and we can use it. Similarly, then left going to left plus plus and right is going to right plus plus. So now I will go to this point. Now at this point, we need to remove this 3 and we need to add this 5. That will be taken care by this logic. So try to solve some problems using this template and hopefully you are able to do it. Now in here in this case, we have to find the maximum, right? So here instead of doing the sum, I just keep track of the max, right? So maybe some sum is equals to max of current max and this nums of I. And from 0, I can basically remove that element from my window and add that element into the window and check what is the max and dot dot dot. This is the same template. If I write the solution, even you see that this is the idea. Now, the problem here is whenever I maintain this window, let's say for this window, how I can find what is the maximum value we have. So maybe you can use priority queue and max heap basically. And the max heap, the biggest element will be on the top, and we can basically access in the constant time. And that's powerful and efficient. But the problem is whenever we are doing removing and adding, right? So like for this window, okay, priority queue give us the 5, that's fine. And then whenever I move to this window, I need to remove -1 from my priority queue and add 3 from the priority queue. Now this addition and deletion is logarithmic and can lead us to TLA. So for this kind of, there is a special monotonic queue logic, and that is specially meant for this. Whenever you need to find a maximum or minimum element in a window, you can use monotonic queue. The idea of monotonic queue is we just need to make sure in the queue, maybe here I can write. The idea of monotonic queue is we're gonna always put the element in the queue into the decreasing order, right? So something like this, 6, 5, and 2, something like this. And we always know that 6 is the maximum element, the first of a queue basically. We can use deck and the first, I don't know if it's called head or tail, but you understand that the very left thing is the maximum element we can extract, and that will be the constant time. So instead of priority queue, and then addition is also like constant, and removal is also like constant. So instead of going logarithmic, if you use the priority queue, initially in the earlier problems we were able to solve it using priority queue, but now I think LeetCode has done some optimization maybe. At least in Java I get TLA, so you have to use the monotonic queue. So I hope this is clear. So let's write the implementation of our monotonic queue. You can write it here also, but I will write my own class for that. I'm more comfortable. So let's call it like MQ maybe, monotonic queue. And it gonna have, of course, a queue, right? A queue of integer. And what else we gonna have? I don't know. For now, let's do this. I will see if we need anything. Mm. We're gonna have two methods, right? Void add, and then we're also gonna have remove. Okay. I always messed up here. You will see. Even today, I'm pretty sure I will mess up. So, okay, what's the idea? The idea is if we have this element, we have in my queue, we already have elements like this, 6 and 5, and then the next element that is coming is let's say 1. So that's fine. No? We can simply add it into our queue. That's fine. But what if the new element comes like 8? So here I can say something like maybe while queue that size is not equals to 0. Oh my god. Why? And q dot peak last. So this is the very last element, right? So okay, so this is our queue like 6 and 5. Now the element comes is 8. Now we wanted to make sure 8 will be pointed to the very first thing. We need to remove this 5 and 6 because 8 is the greatest of these, right? And we need to maintain that monotonicity. So if um, the element that is coming is greater than q dot peak, we need to remove the elements from the list. So here, let's say my element is coming like 8, right? And we need to remove this 5, we need to remove this 6 because now this 8 is the answer, correct? And yeah, and after doing this, we know that our queue is in the grade shape. So I can just offer last A. I will add this element from the last. I will try to simulate one more time because I always mess up this condition and I hope this is right. So for example, let's say we have this queue like 7, 6, 2, and yeah, let's say this is our queue and the new element is coming is like maybe 5. So 5, so here this 5 is greater than 2, so we will remove this 2 and this 5 is greater than 6. No, so we will not go inside and we just gonna offer 5. Right. Let's say we have another 5. Um, Now this 5 is greater than q. No. So we come here, I can append this 5 and that's fine because it is maintaining the monotonicity. I'm not sure. I think, yeah, I think this will work even for duplicates. And now here I can just check if um mm, 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 q dot size equals to 0, I can just return if there is nothing to remove. And if q dot peak first equals to element we wanted to remove is at the top. Basically, it is kind of lazy deletion. Until and unless that element that we want to remove is on the top, we are not going to remove it. If it is on the top at the very head, then only we are going to remove it. So basically, we are delaying the removals. And I can say like q dot hold first, remove the element from the list. And yeah, I think this is it for now. Let's initialize this MQ, maybe war MQ, new MQ. Now again, this I hope this you remember this one, right? So this is the idea. And we're gonna have list of integer answer, new array list. Then we're gonna for the this is for the initial window, right? I can simply say like int I equals to 0, I less than nums dot length, I plus plus, not nums dot length. We have to go to k only, and simply say like mq dot add nums of I, correct? And in my list I will add mq. Okay, I can write a method here for getting the max. So a utility method public int max maybe max max max. Yeah. And we're gonna simply return q dot peak first. So this is always going to be our max value. And here I can simply say mq dot max, right? So this is, and then so this part is done, right? Now we have to do this part. This Let's do that. Okay, and they're gonna create this for loop. Left 0, right k. Left is less than num start length, or maybe I can just do right because right is always going to be in the right side, so this will work. And then left plus plus, right plus plus. No, the element from this left pointer we need to remove, and element from the right pointer we need to add. So mq um dot add nums of left. Sorry, we have to add from right only, and then mq dot remove nums of left. And now mq is contain the w- elements related to that window, and I can just say answer dot add mq dot max. Here it should be answer, and we will keep doing this, and then we need the answer will contain all these elements which are max, and we have to return into this int array instead of list. So let's do that. So answer dot stream dot, now this is like the box type, I mean wrapper type, so we need to map it to primitive type, right? Integer dot int value. We have a method, then I can simply say to array, and this should work. Yeah, I think let's compile it. Okay, we have error. What? Where? Added semicolon. We have to use this semicolon, not comma. Okay, so 3, 3, 5, 5, and 6, 7 we are getting. That's great. So let's try submitting it. Yeah. So you might say like it's a bit slow, but it's not actually. It's just a linear solution because we are iterating over this element once, and these methods add and remove are nearly constant, right? We are adding, and addition is like at max of like k, like n a big O of k, because in the worst case we might need to remove all those elements and then we add that element that is the very large. So yeah, if you remember this template, you see it's basically based on that only, just a little bit of change of logic and rest is fine. So yeah, I hope you like it. So let's see what questions are there. Okay, this one is hard actually. Sliding window maximum problem. But yeah, this is square root. I hope you like it. So this is the binary search we did. Then this populate a right pointers in each node. This one was BFS. And the sliding window maximum, I think it was hard just because this monotonic queue. If you try to solve it using like priority queue, it might you might get TLE. Sorry. So I hope you like it. Let's catch up in the next one. Thank you so much for watching.